Just as before, we can actually describe the random variables when they're continuous with the help of the expectation operator. The expectation, however, in the case of continuous random variables, takes on the form of an integral. So the expectation of the random variable x would be the integral from minus infinity to infinity, so you integrate over the whole domain of the probability density function f at x, which is now weighed by the variable x. Now, if you want to compute the expectation of a different function, not just x, but some function of x, what this really means is that when you use the weight in the integral, you actually use the function h here. One thing that we need to keep in mind where we're working with random variables that can take on infinitely many values, not just continuous random variables, but discrete random variables as well, at least those who can take on infinitely many values, the expectation does not always exist. Well, with the expected value of the random variable we had seen in the previous video, remember we had the function which was 0 all the way up to 0, then x over 2 all the way up to 2, then 0 the rest of the way. It's the expected value then. Well, we need to compute the integral between minus infinity and infinity, not just of the PDF, but the PDF multiplied by x. Before 0 and after 2, there is no PDF value, so we're integrating the function 0. It doesn't contribute to the value of the integral. So here we integrate x times x over 2, this function here, over the interval 0, 2. This is the only place where something is happening. If you do this, well, you have to integrate x squared over 2. You use your knowledge from calculus. The antiderivative of x squared is x cubed over 3. You're dividing by 2 because that's part of the definition of the PDF. And so you have x cubed over 6, which you evaluate between x equals 2, the upper limit, and x equals 0, the lower limit. And if you work it out, you'll get 4 over 3, 4/3. Make sure you know or remember how to get from this to this and from this to this. And what if you wanted to compute the expectation of the square of the random variable? Well, you use the same probability distribution function, in this case, the PDF. And you compute the integral of, if you remember the full formula here, this would have been the integral between minus infinity and positive infinity of x squared, what you're trying to compute, times the PDF. The PDF is x over 2, so x squared times x over 2 becomes x cubed over 2. And when you integrate from minus infinity to infinity, the only part on which the integral can be something other than 0 is what happens between 0 and 2, by definition of this very specific probability density function. If you had another PDF, the bounds might be different. You might have to go from minus infinity to positive infinity, in fact. But here you only need to go from 0 to 2. And the actual value is 2. I've told you that a random variable does not necessarily have an expectation value. Here's a variable which is indeed a random variable because its PDF satisfies all of the conditions. It is always non-negative. In the limit, it goes to 0 in both limits when x goes to positive or negative infinity. The integral of the PDF is indeed equal to 1, but this is not a random variable which has an expectation. I'm not going to go through the exercise with you. You can look at it in the slides. It looks like a PDF, it looks like a CDF. It is a PDF and a CDF. But if you try to compute the expectation, you try to integrate this function here over minus infinity to positive infinity, you will find that it does not exist. The value of the integral is infinity minus infinity, which is undefined. Well, when it's undefined, typically you have to do something else. I'm not doing it here, but no matter how you swing it, you cannot compute a value for this integral. The expectation does not actually exist. If we are trying to remember that the expectation maps to the mean value or the average value, what that means is that this distribution does not have a mean value. If you try sampling observations from that distribution, you compute the mean value, you'll never converge to a specific value. That's really what it means. Well, let's make the link explicit here. The mean and the variance of a continuous random variable. We'll define the mean as the expectation, as before, and the variance and the standard deviation are, again, as defined, the expectation of the square of the differences between the random variable and its expected value, which you can compute more easily using the formula, the expectation of x squared minus the square of the expectation, and the standard deviation of the random variable is again the square root of the variance. And in the discrete case, we had a bunch of relationships looking at linear combinations of random variables. Well, the expected value of a linear combination is the linear combination of the expected values. So that works as we would expect. The variance of a plus bx would be the variance of a plus the variance of bx plus, we're not talking about that here yet, but the covariance of a and bx. The variance of a becomes 0. The covariance of a and bx is also 0, and the variance of bx, well, we've seen this before, that's just b squared times the variance of x. So as long as this a here isn't accompanied by some other random variable, the variance of a sum plus a multiple of a random variable, you can just forget about the sum part. Take out the b, which you'll remember has to be squared. And the standard deviation, as before, would just be the square root of the variance, which is the square root of b squared times the variance of x, which is just the absolute value of b times the standard deviation of x. So things do not change on that front.